So speaking about higher derivatives first, this is really just notational. So say you've got a polynomial like f of x equals 2x3 plus x plus 1. And one thing that here we go. So one thing that we would like to be able to do is make sure that we can take the derivative of this. So the derivative function says that you take an input x and the output is going to be the derivative of this function at that point x. And we know by now that the derivative is linear. We can break this up term by term. And using the power rule, the derivative of 2x cubed is 6x squared. Derivative of x is 1. Derivative is 1. Derivative of 1 is equal to 0. But you can repeat this process. So you can look at the derivative of the derivative. And that you might call f double prime of x, just to indicate you're taking the derivative twice. And going through the same rules again, you'll get, bring down the exponent 2, so you'll get 12 times x to the 1, which is just 12x. Derivative of 1 is a constant. And you can keep on going. Like you could take the third derivative, and you'll get 12. And finally, the third derivative. And finally, when you take the fourth derivative, you'll get 0. And when you start taking derivatives more than 3, what you'll often see people do is just put a little superscript in parentheses to indicate that they're taking 4 derivatives. So the fourth derivative of this function f is equal to 0. And so are all of the subsequent derivatives. What's going to be true for any polynomial? You take enough derivatives and you'll get down to the 0 function. How would you notate this in Leibniz notation? Well, f prime of x. In Leibniz notation, you would write df dx. And so for the second derivative, you'd write something like d squared f over dx squared. So it's pretty natural, but you have to keep track of where the superscripts go. So you're not taking the derivative of f squared, it's the second derivative. So that's why you say like d squared and then over dx squared. The reason where that notation comes from is because equivalently to df over dx, you could write ddx of f. And when you do this, you're kind of treating the derivative as an operator that acts on functions. So you'll see this alternate notation. And if you do it twice, then you're thinking of like an operator that's acting twice in a row. So what happens when you apply something twice? You think of that as like squaring it. So d time, so like 2 d's, you notate that as d squared, and 2 dx's, you notate that as dx squared. Even though you understand that this isn't literally a fraction, it's a limit of difference quotients, people still like to use the suggestive notation. And so if you wanted to do the third derivative, then similarly, you'd just write d cubed over dx cubed of f. And that's what we calculated was equal to 12 in that example. Okay, and so why would you care about doing that in the first place? We'll learn later on in the class that second derivatives can give us some information. So you most often see a function, its derivative and its second derivative when you're doing applications. Just very briefly, the what does the second derivative tell you? Like if you've got a function like f of x equals x squared, look at its graph like that. And so f prime of x equals x. And so you know the graph of f of x equals x. So let's compare these two graphs for a second. So when x is equal to 0, that's telling you that the slope of the tangent line is 0, which makes sense. And then the slopes of the tangent lines kind of increase linearly. So when x is equal to 1, you have this line of slope 1. When x is equal to 2, the tangent line has slope 2. General principle, so derivative is rate of change. So when the derivative is positive, your function is increasing. When the derivative is negative, your function is decreasing. And you can see that here. So this parabola decreases until the point 0. Its derivative is negative and creeping up towards 0. And then the parabola begins to increase at the same time the derivative becomes positive. So what does that second derivative tell you? Second derivative here is constant, it's number 1. But the important thing, here's its graph, if you like. The important thing is that what the second derivative is ultimately going to tell you is the concavity of the original function. So this function has a property that we call concave up. Compare it to like g of x equals negative x squared, which would be concave down. And your second derivative basically tells you whether you're making this shape or whether you're making that shape. And we'll see more applications of that like later on in the course. But that's just hopefully some motivation for you why like we even talk about second derivatives in the first place. But like they do give us information about the original function. The one more thing that I'll remark on is we also had this physics application from last time, which says like if you have this force due to gravity, which is like well, you could put the minus sign here or not, but there's this near the surface of the Earth, there's this downward pointing force due to gravity. That's an acceleration force, roughly 9.8 meters per second squared. And as we saw, that's like saying that if you're an object in free fall, then you have a constant acceleration due to gravity. And your velocity turns out to be something like a constant, your initial velocity times time, or excuse me, initial velocity times or minus time times your acceleration, and your position was something like initial position plus time times velocity minus t squared over 2 times 9.8. That was from last time. And so all of these things are related because if you take the derivative of position, then derivative of constant is equal to 0. Derivative of t times v naught is equal to v naught, and then minus 9.8 over 2 times t squared. And I know I'm just like rewriting it, but the point is like here I'm taking the derivative of this function, and it's becoming clear to me that that derivative actually is the velocity. And then the second derivative of the position function, which is like the first derivative of velocity function, that's what do? You derivative of the constant is equal to 0, and then using the power rule, negative 9.8 over 2 times t gives you minus 9.8. What did I do? I miscalculated this. So the derivative of position would be 0 plus v naught, and then use the power rule here to get 2 over 2. So this is actually just negative 9.8 over t. There comes my cat getting in front of the camera. So sorry about that. Can't be mean to the cat though. I just have to let him interrupt me. There he is. He's just trying to show some affection there. The cat doesn't care about class. Okay, buddy. Try to gently move him out of the way. See if he'll manage being in my lap instead of on the camera. Yeah, so that first derivative is the velocity. And then that second derivative of position, the first derivative of velocity, is then just going to be derivative of the constant is 0. And derivative of negative 9.8 times t is just negative 9.8. Which is, of course, the acceleration. So the general takeaway there is that acceleration is the second derivative of position. Velocity is the first derivative. Okay. Let me give you a quick practice exercise. So let's take y equals uh, 1/2 x squared plus x cubed minus 4. So please take a moment and calculate d squared dx squared of y at the point x equals 1. So this will help us practice getting used to the notation. So take 1 minute, please calculate the second derivative of y with respect to x at the point 1. I'll check in. Okay, so after giving you some time to think, I'll share my answer too. So take that second derivative. So how do we do that? So you should take the first derivative first, dy dx. It's going to be 2 times 1/2, which is 1. So just x plus 3 times x squared, and then minus 0. And so next, to get that second derivative, you're going to have d squared over dx squared. Sorry, the little guy's still bugging me a little bit. So that second derivative, it's the derivative of the first derivative, and now that's 1 plus 6x. And so this is your second derivative, and you're trying to calculate this at the point x equals 1. And so you can do this just by plugging in the number 1 into this expression. So it's going to be 1 plus 6 times 1. So the answer is 7. Okay. So that's it for higher derivatives. It's basically just knowing that you can take second derivative, third derivative, or however many derivatives you want, and you get these new functions. And we notate them either using primes or using this Leibniz notation. It's displayed there. The other thing that I'd like to talk about today, so it's this question of what is the derivative? Of what is the derivative of sine of x, and also cosine and tangent and secant, cosecant, and cotangent. And let's just try to figure it out. I mean, there's going to be a couple of steps. We'll confront each step as we get to it. Let's try to figure it out. So when we're trying to take the derivative of something new, we don't have much recourse other than to go back to the definitions. Limit definition, limit as h goes to 0 of sine of x plus h minus sine of x over h. So this is the formal definition of derivative of sine. And by the way, not to just completely give it away, but the answer is cosine. So the derivative of sine is cosine. That is to say that the slope of the tangent line to sine of x at the point x is given by the cosine function, which is kind of interesting. But what we're going to do here is try to say, like, how can you see that? How can you actually calculate it from the definition? And I don't know that we're going to get much mileage just looking at this difference quotient. I don't know, like it's hard to work with just sine of x plus h. So what we're going to do is we're going to try to use the, I mean, you could do two different things. Like you could use the angle sum formula for sine to break this up. And maybe that's what we want to do. Yeah, let's try to use that addition formula. So I remember we talked about that. We talked about that long ago. And in fact, and yeah, sorry, I missed a couple questions in chat while I was doing the screen share. I'll try to be more mindful of that as we go along. And so we did speak about this sum formula earlier on in the class, I remember. And so in fact, I'll share the document now that I showed you back then. So if you remember, like if you have sine, in our case, it's x plus h, then the answer is going to be sine x times cosine h plus cosine x times sine h. It's this first identity here. And we even talked a little bit about the proof, how you can kind of envision it by looking at the two different angles and then rotating the triangle that you get down into standard position. And it gives you a difference formula ultimately that you can use to get the sum formula also. And while I'm looking at that, I'm gonna go ahead and write it down, and then I'll switch back to the document camera. But do you remember in your own notes, we had limit as h goes to 0 and sine of x plus h. So that's going to be sine of x times cosine h plus cosine of x times sine of h. And let's go back to the document camera. So you can see I've just applied that angle sum formula, and then we're still subtracting sine of x. And then everything is divided by h. And so what I'm going to try to do is break this up. So I see two terms that have sine of x in them. So I'm going to collect those terms. So that's sine of x. Oops, that's sine of x times cosine h minus 1. So that's sine of x times cosine h minus sine of x there. So that's those two. And that's divided by h. And then what's the term that's left? It's like cosine x times sine h over h. And you're already starting to see it work out, because here you can recognize sine h over h. And this is the function whose limit tends towards 1 as h goes to 0. So we've seen that earlier in the class. So that's actually good. It's looking like the limit as h goes to 0 by the limit law. That's going to be cosine of x times this limit, which is just going to be cosine of x, because that limit's going to be equal to 1. But like, what about this? So hopefully this limit is going to be equal to 0, because if it is, then the limit of the entire thing will just be 0 plus cosine of x, which will give us the formula that we want. So when I look at this, this is sine of x. That's sort of like a fixed constant. X is what you call like a fixed and arbitrary number. It's just your input into the sine. And h is my variable here, because h is the thing that I'm letting go to 0. So I'm trying to take the limit. So I've really got a constant sine of x times this function cosine h minus 1 over h. And then I have to understand, like, what's the limit as h goes to 0 of cosine h minus 1 over h. So cosine 0 is equal to 1. So that's going to be an indeterminate form. It's going to give me 0 over 0. And I really should just investigate what that limit's going to be. And if you watch the video, then you saw that the way you can do this is you can just look at the graph of cosine h minus 1 over h. And you can see that as h goes to 0, this graph also goes to 0. I can show you that on Desmos. So for instance, let's try to get this set up. So for instance, if you look at y equals, what is it? Cosine of h minus 1 divided by h. So that's the graph of this function. And you can see, as we're zooming in, that, I mean, it's not defined at 0, of course, but the limit of the y values is 0 as the value of h heads towards 0. So here on the x-axis, that's different values of h. On the y-axis, we're showing the value of cosine h minus 1 over h. And when we're taking the limit as h goes to 0, we're asking, where do those y values go? They go straight to 0. So that proves that that the limit is equal to 0. Or I mean, like, I guess it's not like a formal proof, like relying on a software program, but it definitely shows us that that's what the answer is going to be. And if you want to be like really more formal with these limits, then we typically push that on to higher level classes like analysis. Okay, so let's go back to our calculation. So we know that these limits individually exist. So let's use the limit law, the addition limit law. And this is going to be sine of x times limit as h goes to 0 times cosine h minus 1 over h. I'm really doing two limit laws at once because I'm using the constant multiple rule to pull out this constant. I mean, there's an x there, but h is the variable. H is the thing being that's changing, that's going to 0. X is like a fixed but arbitrary constant. So I'm pulling out the sine of x, and I'm taking the limit of cosine h minus 1 over h, adding to this cosine x times the limit h goes to 0, sine h over h. And so we just saw from the graph that this function is tending towards 0 as h goes to 0. So here I'm going to have sine of x times 0. And here, on the other side, I'm going to have cosine x times the number 1, because limit of sine of h over h equals 1. So that's cosine of x. So that proves it, that shows it. And there's a similar argument you can do to show that if you take the derivative of cosine of x, you take the derivative of cosine of x, that's going to be the limit as h goes to 0 of cosine of x plus h minus cosine of x divided by h. And you can calculate this in exactly the same way. So what you'll do instead of using the addition formula for sine, what you'll be doing is you'll be using the addition formula for cosine. You can also read it off that, which you can also read off that sheet that I shared, and it's on the Google Classroom too. And then when you do that, and this time you'll be factoring out cosine, whereas last time we factored out sine. And you'll still get two terms, and you'll be able to split it up and do some work. And you'll be able to conclude that the derivative of cosine is actually equal to the negative of sine. The derivative of cosine of x is actually equal to the negative of sine of x. And so I want to challenge you to carry out that calculation yourself. I think it's a really cool exercise. But you end up with these two fundamental derivatives. The derivative of sine is cosine, and the derivative of cosine is equal to sine. So that increases the number of functions that we know how to differentiate. So are there any questions or anything on any of that material? Yeah, so there's a question on, it's the question, how does this part become 0? So this was the function that I graphed on Desmos a few moments ago. And so we basically typed in y equals cosine h minus 1 over h and looked at the graph and observed that when h was close to 0, this graph was close to 0. So we figured out this limit with a graphical exploration. So with that in place, you can figure out the derivatives of the other 4 trigonometric functions. And so like what are all the trig functions? It's sine of x, cosine of x, it's tangent of x, cotangent of x, and it's secant of x, and then cosecant of x. So those are the 6 trig functions. You're probably familiar with sine and cosine. So tangent, we're usually more familiar with also. That's sine over cosine. And cotangent, what is that? Isn't that like cosine over sine? And secant isn't that 1 over cosine? And then cosecant is 1 over sine, if I remember correctly. And what I want to say is that using the quotient rule and using your knowledge about the derivative of sine and cosine, you can now calculate the derivatives of all the other 4 trig functions. And I'll show you an example. The first one that people show is that the derivative of tangent is secant squared of x. So that's a pretty common one. I showed that in a video that I posted online for you to watch, so I'll skip that here. But I'll try to show something else. So I could show you like what's the derivative of cotangent. So I can show you what's the derivative of cotangent of x. So you're on a test, it says like show me how to derive the formula for derivative of cotangent of x. And so how can you do this? So you go back to the definition. Cotangent was cosine x over sine x. And you're taking the derivative of this. And you have to kind of remember the quotient rule. And so what is that telling us? So remember the quotient rule. You have a quotient of 2 functions. That formula, it's like derivative of the numerator, the top one, times denominator, minus f times g prime, divided by g squared. So based on my memory, that's the quotient rule there. And I want to apply that with f equal to cosine x, g equal to sine x. And so derivative of f, so derivative of cosine, that's negative sine of x times derivative times g, that's sine of x. And then minus f, which is cosine of x, times g prime, that's derivative of sine, that's cosine, divided by g squared. So that's sine of x times sine of x, that's sine squared. of x. Just plugging into the quotient rule. And remember our notation for sine x times sine x, that's sine squared of x, and then minus cosine squared of x, everything divided by sine squared of x. And here something should be alerting us, I guess. So always be on the lookout for trig identities that you can use to try to simplify your expressions. And so this one, I'm noticing minus sine squared plus cosine squared. And so this is, sine squared x plus cosine squared x, that is equal to 1. That's this trig identity that just comes from the definition of the unit circle. So I can rewrite this as -1 over sine squared of x. So that's the derivative of cotangent. But if we want to rewrite this in terms of the 6 trig functions, so I'm remembering that cosecant is 1 over sine. So 1 over sine squared, isn't that 1 over sine times 1 over sine? So this is actually equal to negative cosecant squared of x. So these two things are the same. So part of facility with these trig derivatives is recognizing trig identities when we see them, and also making sure we remember these definitions. So cosecant x, 1 over sine x. This is cosecant times cosecant, and then a negative sign. So that's cosecant squared. And so let's record what we've learned. We've learned that derivative of sine is equal to cosine. We've learned that derivative of cosine is equal to minus sine. We've learned that, or at least from the video we watched before class, we learned that derivative of tangent is secant squared, and the derivative of cotangent is negative cosecant squared. That's what we just figured out. And so there's 2 more. There is derivative of secant. And there's derivative of cosecant. And so you may be noticing some pattern, which is cosine and negative sine, and then secant and negative cosecant. And it's going to continue here. So I've got, in each case, the trig function and its cofunction, like sine and cosine, tangent and its cofunction, which is cotangent. So to switch the derivatives, if tangent was secant squared, the derivative of cotangent, I switch secant to cosecant and give me a negative sign. And I switched cosine to its cofunction and put in a negative sign. And here, once I figure out the derivative, I'll be able to use that pattern to try to guess what this one is. And we'll talk more later in the course about why this pattern is here, but like I challenge you to think about that too. So what's the derivative of secant? So secant, derivative of secant, that's the derivative of what? Secant was 1 over cosine. So let me make this an exercise for you. Please take a few minutes. Please use the quotient rule to figure out a formula for the derivative of secant. Be welcome to chat me any questions, and I'll check in a couple minutes. Okay, after giving you some time, let's try to work it out together. So I'll try to use that quotient rule. So this is my upper function is f and the lower function is g. So derivative of f is actually 0 times cosine x, and then minus f times the derivative of g. So that's derivative of cosine is minus sine, and then divided by g squared. So that's cosine squared x. So I'm getting here sine of x, because 0 minus sine, divided by cosine squared x. And the way we like to write this, I'll notice that's 1 over cosine times sine over cosine. So this is actually going to be secant x times tangent x, which tells me that the derivative of secant is secant tangent. And if the pattern follows, switch to the cofunction and put in a negative, then the derivative of cosecant should be negative cosecant cotangent. Because look what I'm doing in each case. Like for the derivative of the cofunction, we are switching to we are looking at the derivative of the original, then switching it to the cofunction, putting in a negative sign, switching secant to cosecant, putting in a negative sign. So derivative of cosecant, I should take derivative of secant, switch to the cofunctions, and put in a negative sign. So there's a question mark for like whether that's true. And let's see. Let's try to check it out. So let's take cosecant derivative. That's 1 over sine. And using that quotient rule, again, I'm getting 0. Derivative of 1 times the lower function sine minus 1 times the derivative of sine, which is cosine x. And then dividing by g squared, so that's sine squared of x. So it's looking good so far, actually. So this is going to become, getting some cat hair out of the way there, this is going to become negative cosine of x, because 0 minus cosine of x, divided by sine squared of x. And so I can rewrite this now as negative 1 over sine of x times cosine x over sine of x. And so this is going to be equal to, well, 1 over sine, that's cosecant. So it's going to be equal to negative cosecant of x times cosine over sine, that's cotangent. So it totally worked out. So here's our 6 trig functions and their derivatives. And what I suggest to you, like as a way to memorize this, is that you really only need to memorize 3 of them, because the others will follow from the pattern. Derivative of sine is cosine, derivative of tangent is secant squared, derivative of secant is secant tangent. And then to get the derivatives of the cofunctions, take the derivative of the original, switch it to its cofunction, and put in a negative sign. To get derivative of cotangent, take secant squared, switch it to cosecant, and put in the negative. To get the derivative of cosecant, take secant tangent, turn it into cosecant cotangent, and take the negative. And so the question is, Like the question then is like, why is it true? Like, why is that true? Why do we keep seeing the pattern? And I'll, oh, yeah, here, here comes my cat again. Well, I mean, we're close to the end, so I think I'll just let him sit there. The question is like, why does that pattern happen? And anybody who can figure it out and write up a little like one paragraph explanation, I'll give you some extra credit for that. And maybe we can discuss it later on in the course. So Ghost is telling me that it's definitely time to end for today. So we'll go ahead and do that. So thank you, everybody. Have a great weekend, and I'll see you on Monday. Remember, we've got some homework due this evening. Be welcome to email me any questions about that. So take care, everyone.